In these problems, we're finding the limits of rational functions at what is called a removable discontinuity. Sometimes there are graphs like this one. If you were to actually graph this on a graphing calculator of some sort, it would basically look like a cubic. But at the point 0, it wouldn't be defined because we have this 3x on the denominator. So wherever 0 is going to be on this one, there should be a little empty hole. So at that one point, the function doesn't exist. But you could probably see pretty clearly from a graph what the limit was, because you could see very close on each side of that. However, we don't have the graph. We've just got the equation or the expression here. And we can still use some clever algebra techniques to figure this out. If you have a polynomial, you can almost always find the limit just by evaluating the function at that point. So what we want to do here, we know that the function is not defined at 0, but we want to be able to change something about this function algebraically so that we could put 0 in and calculate a value. In this case, what I notice is that I can factor on the top, I can factor out an x. So if I rewrite this as 3x cubed minus 2x plus 3, and now all over 3x, then I could actually cancel those x's. Now I do not have x on the bottom, and I could evaluate this at 0. So I'm going to do that. This becomes 0, this becomes 0. I get a 3 on the top and a 3 on the bottom. 3 over 3 is 1. So the limit of this function as x approaches 0 is 1, even though the function itself is not defined there. Factoring is definitely a good thing to look for. Sometimes other strategies are required. Let's take a look at this one. I've got this expression, negative 2 plus h quantity squared minus 4 all over h, and we want to find the limit where h approaches 0. We can't just evaluate this at 0 because that would turn the denominators into 0. That won't work. And it also doesn't look like I can factor things out here. I think what I'm going to try is to just multiply out this binomial here, the negative 2 plus h quantity squared. So let's do that. I'm going to just write it like this. Whoops, this is a 2. And we're going to FOIL that out. So let's try that. Negative 2 times negative 2 is a positive 4. H times negative 2 is minus 2h. Negative 2 times h is minus 2h. And then h times h is h squared. And then I've got my minus 4, and all of that is over h. And something good has happened here. I've got a plus 4 and a minus 4. So those go to 0. And I can combine my other like terms here. I've got an h squared, and then I've got negative 2h plus negative 2h is negative 4h all over h. And again, I can factor out an h up top. So h leaves me h minus 4 over h. We can cancel that out. Now I can plug in 0 for h, and we've got negative 4. So the limit to this thing as h approaches 0 is negative 4. That's a little work with finding limits of rational functions at removable discontinuities.